You're live. All right. Welcome, everybody. How are you? Another day. Hopefully, doing okay. Washing those hands, staying clean. So we are going to keep moving along with this kinetics unit. We're making great progress, but of course there's nobody in the room. So that's taking lead a little bit. So we're going to be moving forward. We talked yesterday about the idea of calculating an average rate. That was the, 2 days ago, I guess. 2 classes ago, we talked about average rate. And then yesterday, what did we talk about yesterday? Something sounds about right. We talked about the rate relative to stoichiometry. That's what it was. So we know that the rate of a reaction is related to the stoichiometry. And then today we've got one more sort of concept. This one we kind of came across a little bit earlier. At least large portions of this one we covered in our review. I felt that the potential energy diagrams have been something that were looked at a previous time. So we did do them a little bit in review, but we are going to cover the ideas of collision theory, which is really important theory for describing chemical reactions. So collision theory is a theory. It's an effective theory, especially in gases, for predicting chemical reaction and the rate of reaction, based solely on the idea that they're on 3 conditions. The idea that particles need to collide to react, and that they must also collide with enough energy so that they can overcome the intramolecular forces. So those are the forces within a molecule. And they must also collide with the correct orientation to form the new chemical arrangement. So this is a very fun, interesting concept, I think. I'm going to give you a second to write that all down.
Are we talking about those large particles such as are we talking
We're talking about full large particles usually. Yeah. So we're talking about full-size molecules interacting. And I'm looking for one of these kind of things. Yeah, that works for me. So here's an example that we can look at for how this might look for 2 different energies, for example. So it says it requires a certain amount of energy to overcome the intramolecular forces. In this case, we have a water molecule, or we have probably NH2, I guess, and an oxygen. And these molecules are coming together. If they have low energy, so notice the temperature here is only 100 Kelvin, then the amount of kinetic energy they have is low. So as they come towards each other, they either just pass by each other. I don't quite like that they pass by. They should just bounce into each other. And they would just kind of bounce into each other and they wouldn't actually interact. There might be some exchange of kinetic energy. Maybe the nitrogen or the sulfur, maybe it's sulfur hydride, or would go a little bit faster, or the oxygen would go a little bit slower, but there's no chemical reaction that happens. If instead there's enough kinetic energy, then as they pass by each other, then there's the one chemical can actually steal the other one away. So it can overcome that chemical bond. Not the best version of that in the world, but it's okay. That's kind of the idea. I'll keep looking. I'll let you keep writing. Okay. Yeah. Side. Okay. So, in this way, we kind of, let me think, see if I have more. Yeah, I'll put this picture. Just wanted the picture. Okay. So what we want to think about is this little picture here at the bottom of the page. So here we have two reactants, whatever, ozone here and nitrogen monoxide. And as they come together, if they, for example, came together where the two oxygen atoms are pointing at each other, the orientation is not correct because oxygen is electronegative and oxygen is electronegative. So both oxygens very electronegative. They're holding on to their electrons very tightly. So there's no attraction between the electrons. The electrons cannot sort of jump over and form a new bond between the two oxygens. It's just not likely in this arrangement. If instead the nitrogen and the oxygen were switched positions, then as they come towards each other, then the nitrogen, which is a little bit positive, and the oxygen that's a little bit negative, do have an attraction to each other. The electrons will jump ship, and then this very weak bond between this oxygen pair will break, and you'll be left with nitrogen dioxide and regular oxygen, which is a fairly stable molecule. So in this way, the orientation matters. If they don't fit together nicely, then we won't get a chemical reaction. So let's see. Let's think about if we can think of an example here that I can play around with, and let's see if we can do an extension on that as well. So how about in this example, right? We talked about this is rocket fuel. Can you reason out now why rocket fuel might be a very effective fuel from the idea of orientation? Yes. Oh, these are actually the reactants. Yeah, they're going to form water. We're going to take two of these. Well, why might this reaction occur very quickly if you think about orientation? Just orientation as being a factor. Sure. I was thinking more that even just looking at these as sort of like symmetrical pieces. So thinking about this previous example we were talking about, we have something like, or I guess the example that we just did has ozone plus nitrogen oxide. And they're showing that there's a way that this cannot happen, right? If the oxygen and the nitrogen are pointed this way, then there's no chemical reaction. We don't have that problem in rocket fuel, right? In rocket fuel, I can flip this oxygen all I want. It's always the same. So that also contributes to how fast the chemical reaction is in rocket fuel compared to the slower decomposition where we have one orientation that's bad, one orientation that's good. So that's how orientation and reaction rate are related. Okay, so let's take it one step further. What if we want to use a protein inhibitor? So a protein is like this, and then it has like one little chemical position right here. That's the active site, and then you have your drug. It looks like something like that, and probably this piece has to fit into this hole. Rate fast, rate slow. Yeah, slow, right? It's kind of like docking a spaceship or something. You don't see them, in movies. They're not like flying a spaceship into the space station all willy-nilly, or like if you think Apollo 13 or something. Maybe that's not the one that's good. Apollo 11, the mission that worked. They're very slowly positioning and trying to get it in there. And these are, of course, not smart things. They just bounce around. So chemicals that have to inhibit a protein, usually what we do is, if it's a human being, you just flood them. You give them a big dose, right? 200 milligrams or whatever. Not all that 200 milligrams is there to react. Only a very small amount of it is actually getting in and affecting the protein. But we just send a whole bunch of them in, and we have a small chance that one of them slides into that hole the right way. Overwhelm the molecule, and one of them slides in and hits the right spot. So that's where protein inhibitors and acting. Someone asked about biochemistry the other day and why it's so difficult. This is one of the reasons, is that you're dealing with huge molecules where you have to figure out what on this massive Death Star of a molecule is like that little porthole that we have to fit the chemical through. Exhaust vent. That's what it was. Exhaust. So that's orientation. Now the other concept to overcome is chemical bonds. The actual force between the molecules has to be overcome. So when you introduce this, this hydrogen is flying towards this oxygen. This oxygen is flying towards this hydrogen. They have to have together enough energy that they can break one of these bonds. Probably in this case, it's the hydrogen bond, because oxygen is actually a double bond, so that's a very, very strong bond. So all you have to do is you have to have enough energy to overcome this hydrogen bond, to break it, because you're going to be left with usually something like this. Maybe positive, no. Probably something like that. Think about positive, negative, extra electron. Maybe like that. That might work. Yeah, because then you got a peroxide there. Okay. So, there's a whole bunch of possible results, but you're essentially going to be trying to get this molecule close enough. Oh, you're going to go minus on this. That steals. That gives you a slight positive over here, probably, which is really weird. Anyways, I'm not exactly sure about my mechanism for alkoxy. You can usually only break one bond at a time, and usually you're only adding one atom at a time. So when we get to reaction mechanisms a little later in this unit, we're going to think a little bit about this. I won't have you predict anything too complicated, but you can only usually move one sort of bond at a time. So I unfolded this bond over here and used it to attract this hydrogen. And then, I don't know, it might work that way, it might not work that way. And then this one would find another partner. Could also break. Okay. But you still are breaking a bond. So in order to break the bond, you need energy, and you need energy enough to cause that to happen. So I'm just going to check my stream here. Okay, great. Glad to see some people on there. Okay, so this initial bond breaking action is what's called an activation energy. So that is this initial amount of kinetic energy that you need to start the bond breaking process. So not only do the particles need to collide with the correct orientation or correct geometry, they must collide with enough energy. The chemical reactions involve the making and breaking of bonds, which requires energy. If colliding particles do not have sufficient velocity, they will not produce a reaction. So kinetic energy is derived from velocity. So if you are a real physics nut and you want to talk about kinetic energy, the formula is 1/2 of mass times velocity squared. We don't need to play with this too much, but that is the reaction. It can sometimes be useful to have that in the back of your mind. I won't even put it in the final notes. So. That's a lot of your commitment. I can't believe I actually have good numbers in this class. So, thank you all for braving the wilds to come in here. T1. Yeah, I'm gonna put a T2 in a second. So I believe we played around with one of these curves at an earlier date, but I could also be misremembering. Thought so. Yeah, I think that we talked a little bit about. Well, that's a little bit of a different curve yet again, but so for any set of chemicals, for any matter at any given temperature, our collision theory actually predicts that the particles have an infinite range of kinetic energy. There are particles in this room that are moving at nearly 0 meters per second, and there are particles in this room that are moving nearly the speed of light. Number of particles. Yeah. So there's an oxygen in this room that is zipping across the room at nearly the speed of light. At the same time, there's another oxygen that's barely moving at all. And if they both collided with each other, then they would both be moving at about half the speed of light, because it would be taking an average speed. And then they would bounce into some other particles, and then those particles would split their speeds, and then those particles split another speed, and then maybe, and if you take all of those particles and consider all the ways that they can interact and bounce off of each other, you end up with this type of distribution, where the majority of the particles are in some sort of average kinetic energy, and then there's this small trailing tail that never reaches 0 that goes out towards infinity, where these ones have nearly infinite speed, right? Way over there, there's they can go nearly, well, not infinitely fast, because the speed of light is the top end of that, but they can go, there's up to their maximum speed. But this is like a microscopic amount, right? Much less than 1% of the particles that are moving really, really fast. So this is at some given temperature. What will happen if I heat the temperature up? How will the distribution change when I heat the temperature up? Where will the lump move?
I think the lump will go sideways.
You said sideways, and then you open your hands like this, so that sounds like it goes both ways.
Well, yeah.
Do you think the lump moves this way, or moves this way, or goes up or down?
First one.
Let's do cooling down first. Cooling down is easier. So what happens if we cool it down?
We go to my left.
So your left, yeah. And what about the width of the lump? Great. And the height?
It'll stay the same.
Remember, it has to have the same amount of stuff. The integral has to be the same. So we have to have the same amount of if we were making it out of the same, if we were cutting this out of paper, we'd use the same amount of paper. So if you make it narrower, yeah, very good. It can sometimes be difficult to wrap your head around, but it does have to go up. So as it cools down, so let's just call this, even more specifically, let's call this M for middle, maybe. TM middle. And then let's go to TL. TL for low. And we're going to go low is going to be a little bit taller. Wish it wasn't taller. Good, and kind of like that. So TL, the temperature, the grouping moves backwards a little bit, and it gets a little taller. It's not my most beautiful curve ever, but I'll have to do. And so now what do you think about T high, the high temperature range?
Do the opposite. You go to the right, you shrink down.
And so T high, yeah, will be something that looks more like and if we took the average kinetic energy, they're going to be somewhere in near the middle of this hump. Is your average or KE average? I realize now that I should be using my Zoom so that I can actually write without making a big look like it's not horrible. Okay, so this is going to be my temperature low, and this will be my kinetic energy average. So in this way, what do you suppose? I believe we talked about this a little bit before, but what is, when we measure temperature, what are we actually measuring? Correct. And particularly when we report our temperature, so if I report that it's, minus 2 degrees today, I'm actually reporting the average. I'm reporting this number. So when I said it's minus, it's minus 8 today, I'm reporting this little average kinetic energy. That's what my thermometer is detecting. My thermometer is actually technically detecting all of these particles, but the thermometer on average is getting this kinetic energy average added to it or taken away from it, and the thermometer is sticking at a certain value once it hits equilibrium with the environment. Put it in some boiling water, it's getting more particles are hitting it that are moving faster and transferring more kinetic energy to that thermometer, so the thermometer energy's average kinetic energy moves up. I probably should be a little bit over there. That's okay. All right, so then we add in this activation energy, the idea that there is only certain energies where the chemical reaction is effective. So we can let's put our activation energy right here. You know what, let's do a solid line because my dotted lines are not nice. So this is usually where we would put something like activation energy, and we're going to call it EA. And so when we compare these three chemical reactions, or the three temperatures, we can see that in the green line, there are still some particles that are above the activation energy. But not nearly as many as in our high temperature line. And this is why when we increase in temperature, we typically get an increase in chemical reaction. Because we have, on average, more particles that are available that can react.
Let's see.
Activation energy.
Shouldn't it be?
Hmm?
Shouldn't it be AE?
It's an energy of activation.
Okay.
you're gonna have a lot of E's to compare. So even kinetic energy, honestly, like most chemists would write E with a little K on the little tail, you know, like you could do like, can't even do it myself, but you could do like EK like that as kinetic energy, and then always use E for energy. Yeah, they use EK, right?
They use same forces.
Oh yeah, we use forces a lot in physics. Energy and forces are not quite the same, but they're similar.
I mean the same notation.
Yeah, that's true. Yeah, so forces and yeah, exactly. So in physics, we always use an F for forces, and we try not to put more than one letter underneath it and all that sort of stuff. Yeah. As you kind of, as we let you drift towards your eventual area of study, you can become more and more specific with your notation as you need it. I won't be we'll use whatever works for us right now. So, what else do I have to say about this graph? It can be a little bit tricky to work your mind around this because we are dealing with large numbers in this case, right? So we are dealing with, a box. We have a box and we're having a chemical reaction. We have, thousands and thousands and thousands and thousands. I mean, 1 mole is what, 10 to the 23? 1 mole. That's 1 gram of hydrogen. 10 to the 23. There are definitely more than 1 gram of hydrogen in this room. And 1 mole is more sand than there is on all the beaches on the world or something. So 10 to the 23 is a number larger than the number of stars in the universe. So there are more in 1 gram of hydrogen. There are more particles of hydrogen than there are stars in the universe. That's 1 gram. You do not weigh 1 gram, right? You are made of many more particles than there are particles in the universe, or than there are stars in the universe. So we think about a box and it's filled with this distribution, right? If this is 1 mole, even if this is 50% or 50%, that's still half as many. It's more than half. It's it's still a lot. It's a lot. It's a lot of particles that are active, and these particles all jumping around. So we kind of want to think about them like instead of drawing the same sized arrow on all of my little particles here, I want to draw different arrows on all of them. They're all bouncing around. If they collide with one of their own particles that they don't have a chemical reaction with, then they can exchange kinetic energy. If they interact with a particle and they don't have enough energy to overcome this activation energy barrier, they can just bounce off of each other and exchange kinetic energy. The other particle goes faster, the other particle goes slower. This is, at least in an ideal gas law, that's the case. And then once in a while, they get close enough with enough energy that they can actually start to move electrons, really, is what happens. So what they're really doing is they're coming in close enough with enough energy that they start to push their electrons onto the other element's electrons, and it's enough energy to jump into a new orbital, to find some new form where the electrons are in a new arrangement so that the particles can be in a new arrangement. That's really, like, if we really had to get down to what's going on, that's what we would do. We can't really look at that in this class, at least, and we can't really look at it very well anyways, but we can do some little doodles and diagrams to kind of to get at what that would look like. So one of the doodles that I like is the potential energy diagram. We can put some extra features on here to kind of get at that. So a potential energy diagram describes potential energy. Remember the previous one was a kinetic energy diagram. So we're now looking at a potential energy diagram. So in a potential energy diagram, we have the potential energy of our reactants and the potential energy of our products drawn out in a vertical manner, and then the chemical reaction itself drawn on the bottom. when these two colliding bodies are coming closer and closer together, what they are doing is, if they are not going to continue to move, well, then that energy is going somewhere. If it's not going into movement, where is it going? If that energy is not going to be kinetic energy anymore, it will become potential. And so we can see the collision happening here. A collision with an appropriate orientation and an appropriate energy is happening in this diagram right here. This is where two atoms with two molecules with an appropriate orientation and appropriate amount of energy are able to start converting that energy into a new potential. So this bump here is from a kinetic energy loss, really. Kinetic energy conversion as two atoms came close together. Yes? They're free, yeah, they're free. So there actually probably is some structure here where you have little lumps as you had to break up some of the hydrochloric acids. Yeah, it doesn't happen all at once. Usually the lumps are on the other end here somewhere. So once that first step is done, then the whole thing starts to fall apart at that point. Let me think about this one. What is going to happen in this chemical reaction? You got magnesium chloride. This is the formed product. I think you're going to have to break that hydrogen and chlorine. Hydrogen and chlorine will be separate already.
So technically there'd be 3 reactions.
Oh, there's a whole bunch. I'm just looking through it right now. Yeah, there's a whole sub section, and I think it's in physical chemistry 1, where you actually would step through and do some calculations here. We do have to there's lots and lots of steps that are involved. For example, we have to think that the magnesium loses its electrons. So that has to happen. And then that will raise the energy of that compound. So, and then it does that again. Which would be 2 plus. So that's 2 electrons that you lose. So you have 1 jump, you got another jump. Then you have the hydrogen chloride has to split to hydrogen plus Cl minus. So there's a little tiny jump there. And then everything else should be gained. So then you're gonna be this will be all the way down, will be, hydrogen plus an electron to give you hydrogen dot. 2 hydrogen dots will give us H2. That should happen really fast. And then the magnesium 2 plus a chlorine. Yeah. So it would be, it would be a lot of steps here to get there, but it would look like something like that. So yeah, that's crazy stuff. That's not actually. That used to be in first chem. That used to be in our first chem. I think it's been moved to the second university chem. So it's not as hard as maybe that looks right away, but it's just thinking about all of the possible steps that would be involved. But I'm going to use that to inform that what I'm trying to say is that up here is got to be some sort of arrangement that's somewhere between the 2 chemicals. So this is what we call a transition state. And probably the most likely transition state, I'm trying to draw one that makes a little bit of sense. They're always made up anyways, but we could kind of think that we're going to have something like, we've got our magnesium here, and it's going to have some sort of connection to the chlorines like this. So it's not quite connected to the chlorines like that. And I guess maybe it's, no, doesn't matter. Anyways, we can kind of think about something like this. So there's at some point something that looks kind of like this, where you've got something in between, right? It's not quite magnesium chloride. It's not quite, it's not quite magnesium and HCl. It's something in between. And this point, this arrangement is going to be very unstable. Potential energy is the energy of arrangements. It's the energy of position. So this positioning of chlorines and magnesiums in a not quite bonding distance, not quite chemical formation distance, this is going to be a very unstable place. And then, maybe we don't have any hydrogen, so we could kind of extend the hydrogen bonds. So essentially all the bonds are real long right now. They're not quite where they want to be, not quite where they're ready to move to the next step. And so this is what we call a transition state. And there's another word that I'm thinking that we use later on that I can't quite remember what they call it. Transition state. The other one is intermediate, right? And so this would be the transition state. This thing up here, if this was what we wanted to call, we might call this an intermediate product. When we go to reaction mechanisms in a few lessons, we'll definitely talk about intermediates. At the transition state, we think about the system as being equally able to return to being the reactants or return to being the products.
So I'm looking at something, but basically, it can still stop the reaction.
Yeah, so now the hump can be a bit of a weird thing to think about too much. We've got the hump here, right? Which often students will think about, okay, the products are climbing in energy up this hump. Like they're pushing, I've even heard it described as you're pushing you're pushing the ball up the hill or whatever. And then it rolls down the other side to get all this energy out of it. That does work, but it does suggest that there's a sort of movement in this direction that is not a little bit of a misnomer. We have to think that if we plotted out the kinetic energy, these kinetic energy diagrams that we had in the previous one, I don't know how well this ever works. I always do. I'll do this every year, but think about on the side here, we could take our line here and our line here, and we can draw out a kinetic energy diagram, but sideways. So this will be number of particles here, and this will be kinetic energy. So our diagram is going to go like this. Oops, that's a reaction that doesn't. So if this is the case, this is a low temperature reaction. Notice that this reaction would not be able to happen because we don't have enough energy to cross our threshold. So let's try that again. Time. It's harder to draw than I thought. That's a little bit longer. Okay, so here we have chemicals that are reacting. All of these are magnesium and hydrochloric acids that are all bouncing around down here, not interacting at all. But only the ones that have a kinetic energy that's over that hump will actually be able to react. And as soon as they react, it should be almost instantaneous. And so any of these particles have the ability to react. So why doesn't the reaction happen instantaneously? They still have to bounce with the right orientation.
What the reaction called?
What does the reaction do? Well, this reaction would be producing this magnesium chloride and hydrogen gas. So this is actually the same reaction we did the other day, right? We put the magnesium and hydrochloric acid, and we saw some temperature. Now, where does the temperature part come from? Remember that when we felt our magnesium chloride, magnesium and chlorine reacting in the test tube the other day, it was hot. So notice that in the production of the product, you have a product that has less potential energy. So you've made a new arrangement of atoms in a way that has less potential energy. If it has less potential energy, what have you created more of? Less potential must be more. There's only two types of energy, right? Less potential energy is more. It's got to be louder than that. Less potential energy is more kinetic energy, yes. So when we go to less potential energy, we have essentially donated this energy into the kinetic pool, which is an interesting idea because now you might actually be able to bump your chemical reaction forward a little bit, right? Some of that kinetic energy is actually going to bump this graphic a little bit up, and then bump a little bit up, and then you'll have more particles that will be above the activation energy barrier. So an exothermic reaction can actually drive itself. So one of the reasons exothermic reactions are very, very reactive is that they can actually produce energy to pump their own chemical reaction. Sort of self-priming. So this is this difference in potential energy. If we compare the original state and the end state, we would say that the difference is negative. It's less than zero. Because you're ending with a small number. Take a small number minus a large number, you'll end up with a negative number. That's what we call an exothermic reaction.
So, forming of like molecules is basically just transfer energy.
Yeah, sure. It's think about it as a transfer of energy to form a new arrangement. Yeah. That's why I really like the definition I use to little kids for chemistry is chemistry is the study of matter and how to change it. And particularly changing arrangements, but I don't get into that with grade sixes. But like changing arrangements of atoms. And to change the arrangements of atoms, you have to put in energy. If I wanted to change the arrangement of this room right now, I'd have to put energy in, right? I'd have to expend energy getting you to stand up, change spots, all that sort of thing. So there's energy goes in, and then the particles get rearranged. And that new arrangement might have more or less potential for chemical reaction. Some really interesting stuff that comes out. I have to, go teach evolution in my later period, and I always think about the beginning of time and how particles must have arranged to form the complicated elements and how that would be possible because complicated molecules have higher potential than composite molecules. But there's a reason. Yes. Overthinking things. Yes. Do you have a question, John?
I was going to say, what's the
Oh, you mean like me putting in kinetic? I'd be putting in my kinetic energy, my effort and will, I guess, to get you to get up and move. Okay, so the opposite, of course, can happen is if you had this type of reaction. So here we have NH4Cl, that's ammonium chloride, reacting with water. This one I can almost predict what the chemical reaction looks like, so that's actually pretty good. So let's do that one. So that one's got a good transition state. So here the water molecule and the chloride are coming together. As they come together, they end up creating ammonium hydroxide and hydrochloric acid, which is an acid and a base together, which is not really a favorable combination. Right? Acids and bases typically react and neutralize each other very quickly. So when you go to dissolve ammonium chloride in water, you'll actually find that the container becomes colder. As the ambient temperature in the water pushes the chemical reaction forward, but you end up creating a new arrangement of ions that have a higher potential. So this is what's called an endothermic reaction. And at the top here, we could imagine something that looks like, we're just doodling. These are not real. But NH4 is a really small molecule. Looks like this, and it has a positive charge. So as the water comes in, water has a slight negative charge over here. So it comes in close to that positive charge, and then it pushes away the chlorine that's on the other end. And at the same time, there's another chlorine over here somewhere. So this might be, gets a little bit more complicated the more of these you put in a row. Something like that. And so this chlorine is also attracted to that hydrogen. And you have to kind of get in here and start weakening the hydrogen bond. So that could be the transition state. Whole bunch of pairs. Got enough water kicking around, you can just stick 1,000 waters in there and it'll all work. Shouldn't be any S's.
The two, I can just put my glasses on.
Like hatches.
I don't.
I'm missing some details here.
No, I still can't read it.
Which one are you looking at?
Above the O.
Above the O? Oh, that's, yeah, you won't know that. Okay, that's that is what is a tiny delta.
Okay.
Yeah, little baby delta. So the big delta is the big triangle. That's like a true change, but a partial change is so a partial change in charge between the hydrogen and the oxygen is a small delta. This one should have a little tiny positive. It's called, that's how we represent partial charge. In the case of NH4, it's a true charge, and it's truly positive. The chlorine is truly negative. It truly has an extra electron. It's truly missing one electron, but the oxygen is just more electronegative than the hydrogen, so it's partially negative, partially positive. Got some real heavy concepts in there. So just throwing those in there. Later on, I only put them in there because I believe in you. I believe in your ability to learn them.
Is it HCl?
HCl. Yeah, you'll get HCl at the end, so hydrochloric acid there. Oh, okay, all right. Well, hot shots at my writing here. Okay. HCl there. Okay. So that would be our transition state at top. Now, in this example, the activation energy is going to be to go from this state down here all the way up to the transition state. So this is called our activation energy. So EA is equal to the energy of the transition state minus the energy of the reactants. Lost our one viewer. How am I gonna get to that thousand viewers, guys? I'll be able to stream right from my iPad.
And do a bigger class.
Yeah. Gotta go back to you then. Okay. Get some thousand subscribers. Okay.
It's just like all of these.
What's that? Yeah, posters all over the school. Watch your chemistry class all through the quarantine. Yeah. The videos will be very different next week if they make us stay home. It's gonna be like, go away, James. Go away, Charlie. the whole time. Okay. Notice here that we have an increase in potential energy. Potential energy has gone up. So then the change in energy, also known as the change in enthalpy, has gone up, which means that we have a positive value. It's over 0. And so this is what's known as endothermic. Delta H is simply the difference between the energy of the product minus the energy of the reactant. That's react. Use whatever words you want. So all I should have done, just lay it on. If we slide back up to the previous image, can you point out the activation energy here? What would that look like? Where would the activation energy be here? Just tell me when to stop for the bottom of the activation energy. Okay. And where would the top of the activation energy be?
Keep right there.
Yeah, so this little gap here, this is the amount of energy you must put in that is above. That's the amount of energy you need your products, your reactants to have. So here, oops. This is going to be our activation. So notice the activation energy barrier is much smaller in the exothermic reaction. So this is going to be pretty typical. And then the exothermic reaction will produce energy. So that energy will go back into the active, into the kinetic energy. Now I'm thinking about my diagram. Yeah. Oh, it's not entirely wrong. Yes, it is. I think maybe this should actually be shrunk up to be like up there, but okay. All right, so this so we've seen the heat of reaction shown on our diagram. So let's talk about what that is. The rate of a reaction is determined by the height of the barrier that the particles must cross in order that they are converted into products. The activation energy is the barrier colliding particles must overcome. As particles collide, they form an unstable intermediate called the activated complex or the transition state. I love the transition state. Yes. I actually don't try much more for you, but you can take me a little bit.
Okay.
And then that's about all I have.
Okay, can I go on your blog or?
Yeah, I'm live streaming the classes too. So.
Okay, thank you.
Okay. Yeah, it's all good. So the activated complex or transition state. I prefer transition state. That's the terminology I've always used and I always learned to use. So state is a very physics terminology. It's sort of the state is like the idea if you could take a snapshot of all of the energy and position of molecules, pressure, temperature, all at a given point, what would that look like? And those, so we can get sort of a numerical, it's not just a picture, but also like sort of numerically, what's the current volume, what's the current pressure, what's the current temperature, what's the current, energy, total energy in the system. So the energy required to produce the activated complex is this activation energy, or the energy required to reach the transition state is the activation energy. The activated complex has a maximum amount of potential energy, but exists for a very small instant of time. It's really a theoretical idea, and it usually can't be captured. There is some interest in capturing transition states. That's definitely like a wing of chemistry that some, especially organic chemists, go into. They spend a lot of time trying to, with the idea that, hey, this chemical reaction produces this product. I wish I had that thing in between. Because if I had that thing in between, I bet I could make this different product. And so there is a whole wing of chemistry that works on trying to capture transition states so that they can use them for other purposes. But it's a very tricky process. So enthalpy, or H, is this is the technical term, is the measurement of energy in a thermodynamic system. It is equal to the internal energy of the system plus the product of pressure and volume. We're going to assume that our chemical reactions are going to occur at the same pressure and volume. So we will assume that we can measure enthalpy directly from our potential energy diagram. In a system that cannot lose mass, the heat absorbed or released equals the change in enthalpy. And the terminology of a thermodynamic system is a system where energy is freely exchanged between particles. That's the dynamic aspect. So all of these calculations and things that we do, usually we're under the premise that we are using a closed system. That means one that the energy can't escape from. This is actually different from anything we can actually do in our lab right now. We don't have any lab materials. We don't even have a calorimeter, which is the closest you can get to a closed system. We could make one with some styrofoam. So I'm looking. Usually there's a bunch of styrofoam cups somewhere people use to make calorimeters. But with some styrofoam, even a coffee cup, you can sometimes get away. You can kind of get a closed system. So, for example, this coffee cup right now is pretty good. Is a pretty good closed system. Any chemical reactions that are happening in here, we could probably treat them as a closed system because energy is not really allowed to leave. The cup doesn't get that much hotter when you put hot water in. That paper cup over there, not super closed, right? You're going to usually, especially like a Slurpee cup, you might get like the Slurpee, like you get the coldness on the side or you get the condensation that happens. And that's evidence that energy is not being retained. But in this coffee cup, I can feel some warmth at the top here, so it's definitely not a perfectly closed system. But if we could get a thermometer in there, and we did a chemical reaction, we watched the thermometer, we could actually probably get a pretty decent measurement of exactly how much energy was being exchanged in that chemical reaction. At the university, we have what's called a bomb calorimeter. It's this big metal container. It looks like a giant coffee cup, honestly. It's not that much different, but it's a big. A pressure cooker is a good example, maybe. It's like an insulated pressure cooker, and you put your chemicals inside this little tiny cup. Like it can only hold like a gram, like less than a gram of stuff. And you put it inside, and you connect like electronics to it, electronic leads, and you can seal it all up and measure how much energy is exchanged. But anyways, hopefully that helps. We're going to move to a handout here before you leave, which is to look at that one.
The one on the table?
Possibly. Yes. Thank you. There you go. So I'll try to post this this one online. There it is. So this will be the handout. So you can take that as you leave. And I probably shouldn't touch them. It's really what- you know.
Give us all pictures.
Yeah, yeah, well, these are pretty fresh. So do this for tomorrow, and please, we'll see you tomorrow. I will be hopefully getting our equilibrium booklets in the mail today. They should come from the printer today, and then tomorrow you can pick those up. And I will print off some reviews for both units. We're gonna try to do equilibrium online for the 2 weeks while we're gone. So we'll see how that works. It's a difficult unit, but it's not impossible. So we'll see. Okay, thank you.
Can I get a handout for yesterday?
Yes.
It would be curious, like, the zombie apocalypse.
Don't say that.